Hi guys, welcome to 247 Trends TV, trending 24/7. Alright guys, so in today's video we're going to be watching what actually happened to the Oceangate Titan sub. This is deep analysis, so sit down, watch, and drop your comments in the comment section at the end of this video what you think about this video.
On June 18, 2023, Titan, a deep ocean submersible, imploded during a voyage to the Titanic wreck site, killing all 5 occupants on board, including Stockton, who was the founder and CEO of Oceangate, an American privately owned company in Washington that provides crewed submersibles for tourism, industry, research, and exploration. We'll explore what major factor could have led to such a catastrophic implosion in this video. And it was not just the external pressure. Exploring the deep oceans poses several challenges due to the harsh and extreme conditions found at great depths. But the biggest challenge is the pressure. As depth increases in the ocean, the pressure exerted by the water column increases significantly. At a depth of 1000 meters, the pressure reaches more than 100 times the atmospheric pressure, and at 3800 meters, where the implosion of Titan occurred, it reaches over 370 times the atmospheric pressure. This is equivalent to loading a square foot of surface with over 785,000 pounds force. Designing and constructing vehicles or structures that can withstand these immense pressures without compromising integrity is a complex engineering task. In 2018, a professional trade group warned that Oceangate's experimental approach to the design of Titan could lead to potentially catastrophic outcomes. Although many experts could argue that the spherical structure for submersible would be a better choice, as curvature of the sphere allows for an even distribution of the pressure load, resulting in a more balanced stress distribution, while in case of Titan, its large internal free space combined with the elongated shape is susceptible to stress concentrations, accelerating fatigue and delamination loads. The elongated shape of a submersible is generally designed to optimize its performance and functionality in deep waters. While the specific design consideration and structural integrity of Titan, as far as its shape is concerned, would require detailed information, the elongated shape itself is not inherently a limiting factor for withstanding loads in deep waters. In fact, many submersibles designed for deep sea exploration have elongated shapes to enhance stability and hydrodynamic efficiency. The unconventional combination of materials used in Titan posed much higher safety risks, as the material tend to weaken over the course of many pressurization cycles due to fatigue. Fatigue failure is a failure that occurs when a material undergoes repeated loading and unloading cycles, like Titan's 5-inch thick hull experiencing a repeated stress with changing hydrostatic pressure over the course of a number of previous dives that it underwent. Fatigue failure can manifest as gradual growth of microcracks or delamination within the structure. These cracks can propagate and eventually lead to catastrophic failure if not detected and addressed. But let's get back to the basics. This disaster could have been avoided with the right engineering decisions. Oceangate promoted Titan's carbon fiber construction with titanium end caps as more efficient to mobilize, being light in weight compared to other deep diving submersibles. It also said the vessel was designed to dive 4,000 meters with a comfortable safety margin. But carbon fiber composites can have multiple issues that we'll see in a minute, especially when they are subjected to extreme pressures like the one that Titan underwent. They can be stronger and lighter than steel, making a submersible naturally buoyant. But they can also be prone to sudden failure under stress. Non-destructive testing of Titan's hull was therefore absolutely necessary to ensure safety. Ultrasonic testing could help spot areas inside the structure where the composites had cracks. But the company claimed their technology, developed in-house, used acoustic sensors to listen for sounds of carbon fibers in case of hull deteriorating, to provide early warning detection for the pilot with enough time to arrest the descent and safely return to surface. This, according to me as a mechanical engineer, is the biggest mistake, as acoustic sensors would provide a real-time deterioration of carbon fiber. What if the orientation of carbon fiber in the structure itself is misaligned and goes undetected? What I mean to say is carbon fiber composites exhibit different properties when subjected to compression compared to tension. Note how the fibers buckle under compression. This is due to the anisotropic nature of carbon fibers. meaning that the material exhibit different mechanical or physical properties in different directions. The most important point to note here is the fiber direction. When the load is applied parallel to the fibers, the composite exhibits higher strength and stiffness, making them highly effective in resisting forces that attempt to pull the material apart. But in the transverse direction, that is perpendicular to the fiber, the mechanical properties are relatively lower compared to the fiber direction. This is because the load is not effectively carried by the fibers in this direction. Instead, the matrix material primarily supports the load, which is generally less stiff and weaker than the carbon fibers. See how the fibers are oriented in the hull of submersible in this video from Oceangate. The carbon fiber is being rolled along the circumference of the shell. As already pointed out, the load-bearing capacity of the fiber is poor along the transverse direction, so any misalignment in fiber can easily initiate deformation with the application of extreme pressure or fatigue. To better understand this, let's take a very simple model of Titan. If we take only the carbon fiber shell, the hydrostatic load on the shell can initiate deformation in the portion where fibers are weaker or poorly aligned, but pressure alone could not have caused the implosion of the shell. This is because the deformation of the shell from any side would cause tension on one side of the fiber layers. This can be visualized from an exaggerated view in which a fiber experiences tension on the bottom side when a force is applied from top. And carbon fibers are very good in taking tensile loads along the fiber direction. But the same deformation can also cause an increase in pressure inside the shell itself that can lead to sudden increase in stress along the shell circumference. This stress is both tensile and compressive in nature. Though the carbon fiber can handle tensile stress quite effectively, the radial stress, that is compressive in nature, is maximum on the innermost layer and can buckle the fiber, thus aggressively accelerating the collapse of the shell. All this in just a millisecond. Oceangate was also warned that a lack of third-party scrutiny of the vessel during development could pose catastrophic safety problems. Apart from this, there's something more that adds to uncertainty while dealing with carbon fiber. The engineering design process for any product usually starts with computational modeling. But the anisotropic behavior of carbon fiber composites adds complexity to the modeling process as the material properties need to be defined and represented correctly in the model. On top of it, carbon fiber composites can have variations in fiber orientation, resin distribution, and manufacturing defects. These variations can be challenging to capture accurately in computational models. It's not that the management was unaware of these problems. David Lockridge, Oceangate's former director of marine operations, said in a 2018 lawsuit that the company's testing and certification was insufficient and would subject passengers to potential extreme danger in an experimental submersible. In January 2020, Rush, in an interview to GeekWire, admitted that the Titan's hull showed signs of cyclic fatigue. Because of this, the hull's depth rating had been reduced to 3,000 meters. But during 2020 and 2021, the Titan's hull was either repaired or rebuilt by two Washington state companies. The entire craft, controlled using a video game controller, raises a serious question on the reliability of the craft, as any delays or malfunctions in the communication or control signals between the controller and the submersible's actuators or thrusters could lead to unintended movements or loss of control, potentially compromising the safety of the mission.